Imagine a game where the math guarantees you make money on average. The expected value is positive, yet you can still go bankrupt. How's that possible? To understand this, we need more than just the mean. We need to understand variance, the law of large numbers, and what happens when bet sizes collide with limited capital. So today, we will discuss mathematical expectations and Bernoulli Trials, and discuss the overall context that ties up the previous videos we've had, wrapping it up with the law of large numbers and applied probabilities. Let's begin with the discussion of mathematical expectation. Suppose we play a simple game with probability 50%, you win 120 bucks. With probability of 50%, you lose 100 bucks. What is the expected value E of X? Hold on, what are mathematical expectations in the first place? Well, quickly, it's a long, heavy-sounding phrase that really means nothing more but the weighted average of a set of numbers x, as referred to by whatever is inside the parentheses or brackets, multiplied by its probability. So here's the formula. You'll notice that this is nothing more but the mean of x, since it's just the weighted average. For example, the average of 120 and negative 100 is 120 plus negative 100 divided by 2, which is equal to 10. Where the probability is 1/2 for each, which we can write down as follows. 120 plus negative 100 over 2 is equal to 120 over 2 plus negative 100 over 2, or simply 100 times the probability 1/2 plus negative 100 times the probability 1/2, or the summation of x times p of x, where p of x is the probability and x is the payoff. Formally, the formula for mathematical expectation, also called expected value of a discrete random variable x, is simply the sum of each possible value multiplied by its probability. So here, E of x is equal to 0.5 times 120 plus 0.5 times negative 100 is equal to 10. And here's the tip. Whatever you see inside the bracket after the E, you multiply each of those to the probability. That's what this does. Now, this tells us if we could repeat this game many times, the average gain per game is 10 bucks. So far, everything sounds good. But the expected value alone does not describe how risky the game is. Now, let's compute the variance of this game. We remember that the variance is nothing more but the weighted average of the square deviations of x from its mean. So we simply put that, the square deviations from the mean, in the expectations bracket. So var x is equal to the expectations of the squared deviations from the mean, and we have this formula. Therefore, their variance is equal to the gain or loss squared times the probability, and then sum it all up. And for that, we have 110 squared times 0.5 plus 110 squared times 0.5, or equal to a variance of 12,100, and therefore the standard deviation is square root of 12,100, or just 110. Notice something important. Expected gain per round is 10 bucks, but the typical fluctuation per round is expected to be around 110 bucks. This means the noise is around 11 times larger than the signal. Yes, the game is profitable in theory, but in the short run, losses and gains completely overwhelm the average. The variance tells us how painful the ride can be before the average shows up. Okay, now enter the law of large numbers. It says, as the number of trials increases, the sample average converges to the expected value. In plain terms, play long enough, and 10 bucks per game starts to show up on average, and the variance gets averaged out over many repetitions. Okay, great. So as long as I keep playing, I'll earn 10 bucks on average per game. That's what you're saying, right? Well, not so fast. Let's consider what's called Bernoulli Trials, a fancy way of talking about multi-toss coin experiments considering the total payoffs rather than just the probabilities. For a multi-toss experiment, the total payoff S sub n is equal to the individual x's, x1 all up to xn, or the trials, where they are called IID, or they are independently and identically distributed. So the expected value of S sub n will just be equal to n times the expected value of x. And the variance, nothing more than the sum of the different variances which are identically and independently distributed. Therefore, it's just going to be n times sigma squared. And therefore, the standard deviation is equal to the square root of variance and just sigma times square root of n. Now, the $10 average gain per game here is a positive expectation. But there is a hidden assumption. You must be able to keep playing. The law of large numbers does not protect you from early losses if you don't have enough capital. So let's take a look at 10, 100, and 1,000 and even 10,000 Bernoulli trials and use a normal distribution to find the range where 95% of the values will lie, therefore z at plus or minus 1.96. So at the low range, you're going to have n times expectation of x minus 1.96 times sigma times square root of n. And the high range will be n times expectation of x plus 1.96 times sigma times square root of n. So we have this table over here, and I'll give you time to take a look at this. What's the most noticeable thing in this table? Well, it seems that the ratio of n times expectation of x to sigma times square root of n, the second divided by third column respectively, gets progressively bigger, suggesting that the payoff is worth more per unit of risk if you do indeed get to play this long enough. What's the next point? Well, given the payoffs, 95% of the time, the low range is negative for 10 and 100 tosses, but positive for 1,000 and 10,000 tosses. Great, you might say, well, like you said, that means I just need to play this at least 1,000 times, right? Well, sure, go ahead and play this at least 1,000 times. But remember that losses of 1,156 can happen at the 95% level given 100 tosses. At that point, if you get hit, you can't play anymore if you only have $1,000. So remember our lesson from the last video? You gotta have enough capital to play this game and let the law of large numbers work for you. That means you should have enough money to survive dips in capital. Given this and the low points in the range, if you want to play these games often enough, you need to be able to survive the dips, and clearly, having capital equal to n times expectation of x is not enough to play 10 or 100 tosses, but it's enough to play 1,000 or even 10,000 tosses. And the bare minimum to survive 95% of the time is to have enough capital to offset the negative low points in the range. Interesting, right? Now let's assume we start with a capital of 10,000. What are the expected returns on investments? Meaning, how much do I get if I put in 10,000 capital? Well, that's simply the expected gain over the long run divided by our capital summarized below. And here's the table. Now, given this table, the incentive, therefore, is to have a low enough capital so that ROI gets maximized, but at the same time to have high enough capital to survive tail risk, or the risk of losing streaks, and yet participate in the long run to levels where the returns are very lucrative. That's basically what risk management and capital adequacy is all about in a nutshell. And this is something that parallels what the banks and other financial intermediaries do in their own fields. Just note, for this kind of capital adequacy exercise, Monte Carlo simulations might be useful to take a look at the 5% worst outcomes and have enough capital to survive that, which happens to be, a value at risk exercise. Now, suppose your capital is $1,000. If you bet 100 per round, which is essentially the loss if you lose the bet, the variance is relatively manageable and losses are survivable without long losing streaks. However, if you bet 500 per round, just 2 consecutive losses can wipe you out. So mathematically, scaling up bets scales both mean and variance. But ruin depends on variance relative to capital, not just the mean. Once capital hits 0, the experiment ends and the law of large numbers stop working. Now, this is another way of showing why positive expected value does not guarantee survival. This exact logic appears in finance. Over-leveraged portfolios or concentrated bets or margin calls and forced liquidation, something we can discuss in the future. And even with assets that have positive expected returns, excessive variance relative to capital leads to ruin. So remember, The mean tells you what you expect to get in the long run. The variance tells you how volatile that path is. The law of large numbers works only if you survive. And finally, one should have enough capital so that the law of large numbers can get into play in order for you to hit the expected values. Hope this 4-part sub-series helps you understand the issues of risk management, capital adequacy, and probability theory. If you think this is helpful to other people, kindly like and subscribe to help support the channel and help us reach out to a wider audience. And see you next time!